Good morning. Today we're going to do some real-world applications of exponential functions. So these show up all the time in nature. It's one of the most common forms of growth because remember, linear functions give us constant growth over time. Exponential functions give us proportional growth over time. So anything that grows or shrinks in proportion to how much is currently there, like bacteria that double every so often, or a radioactive sample that loses some percentage of its mass every so often. Those are all great candidates for modeling with an exponential function. I think when we introduced exponential functions, if I have y equals b to the x, most of the time I've been using this shape to draw pictures. But really there's two kinds of exponential functions I want to remind you. If b is bigger than 1, then we get this exponential growth because we want to think of b is the multiplier. Like if b is 1.1, then you're keeping the 1 you already have and adding another 0.1, so adding another 10% every year. So y equals 1.1x would be appropriate for finding out how much is in a savings account if you have 10% interest, for example. So b is the multiplier. So if b is bigger than 1, that's exponential growth. And if b is less than 1, then what we have is this shape. It's like the other shape, but mirrored horizontally, and we call it exponential decay. And I have a few comments on these shapes before we start using them. That really needs to stop popping up. A few comments on these shapes before we start using them. Lost my train of thought. Let's see. Oh, first thing first. Remember, we don't want the base to be negative because then all sorts of unwanted behavior happens. If my base was -1 and I took that to the power of 1/3, I would get -1. But if I take it to the power of 1/2, I'd get I, which is an imaginary number. And since these are real valued functions, that's not okay. So 1/3 works, 1/2 doesn't. 1/4 doesn't either, but 1/5 does, 1/6 doesn't, 1/7 does. So as you approach 0 from the left, you get this behavior where the graph is defined at like every other point, and trying to say what, quote, every other point, unquote, is for the real numbers is a huge pain. So we're just going to avoid that topic altogether because they aren't useful for modeling anyway. So we want these to be real valued functions, and we're going to give them the requirement that the base also be bigger than 0. So exponential decay is when b is between 0 and 1. Like if b was 0.45, then I'm saying every time I move 1 unit to the right, which is typically forward in time, every time I move 1 unit to the right, the graph is shrinking to 45% of its original value, and then 45% of that, and then 45% of that. So it's never going to reach 0 because 45% of a positive number is still a positive number, just a smaller one. But it will get closer and closer to 0 as time goes on, and however close you want it to be to 0, you could get there if you go far enough forward in time. And that's how exponential decay works. Now, I think I've mentioned this trick before, but we're going to use it in earnest today, which is that if I say y equals b to the x, in calculus, this is a difficult function to work with because the slope of this function is going to have natural logs and all kinds of chain rules associated with trying to take that derivative, trying to find out what the slope is. The slope gives you the rate of change, you see. But we introduced this number, excuse me, e is about 2.7182818, and so on and so forth. It goes on forever without repeating. But E has this magical property that e to the x is its own slope. And so if I want to know if my function is y equals e to the x, then that's the y value. That's the current value of my population or what have you. And if I want to know what's the slope of that, well, it's the same as the y value. And that's really convenient. And since rates of change are so important to the analysis of these functions, we'd really prefer to have e as the base for any of these functions. And so we use a little trick. Exponential and logarithmic functions undo each other. So for example, if f of x was e to the x, then f inverse of x would be log base e of x, which we write as the natural log of x. So e to the x and natural log of x undo each other. And what that gets us is a very nice property that when I say y equals b to the x, well, b is the same as e to the power of the natural log of b. Whoop, not x. B. Because if I put b into the natural log, that gets me a number. But when I put that number into e to the x, it undoes the natural log because they're inverse functions. That's what they do, is undo each other. And then I have my original function back, or my original input back, rather. Sorry, misspoke. So then I get b back. So if that's the case, then I can use the nested exponents property to get something really clever. If I say y equals b to the x, then I mean y equals e to the natural log of b. Whoops, that's not where that parenthesis goes. To the x. Maybe I should have had tea this morning. Normally a little bit sharper than this at 8 a.m. Well, what I can say is the nested exponents property tells me that if I have b to the power of m and then to the power of n, that's the same as b to the power of m times n. So here m is this natural log of b, and n is this x. Load. There it goes. And n is this x. So I can say y equals e to the power of the natural log of b times x. If you think back to graph transformations, all the way back in section 3.5, excuse me, all the way back in section 3.5, this is a number that's being, natural log of b is just some number. Incidentally, if b is bigger than 1, let's see here. If we have exponential growth, if b is bigger than 1 versus less big than 1, oh, I'm sorry, I'm doing two trains of thought at once. First, I wanted to say, if we think back to section 3.5, what this number, this multiplier in the exponent does is this is a horizontal stretch or shrink. And possibly a mirror. It'll be a mirror if the natural log of b is negative. And as a matter of fact, if we call this the b-axis for a second, and I know that's a little goofy, but this is the graph y equals natural log of b. We know that the natural log of 1 is 0, so this is the point 1, 0. So what I'm seeing from this graph is that if b is bigger than 1, then we have exponential growth. And we also know the natural log of b is positive. But on the other side of the curve here, if b is less than 1, but of course bigger than 0, so let me write that. If b is less than 1 but bigger than 0, so the multiplier b is saying it shrinks every time we move to the right. If that's the case, then we're on this pink part of the curve, and the natural log of b is negative. So when I make this function e to the natural log b of x, we have a mirror if the natural log of b is negative, which is what we want. If we look back to this top graph here, we want to have a mirror when there's exponential decay, and we don't want to have a mirror when there's exponential growth. And so this is what's going to do that for us. As expected, this formula performs adequately. So, goodness, excuse me. I'm sorry, just a moment here. Maybe this will help. Don't worry, it's not Corona. I haven't left the house in 2 weeks. Instead of writing natural log of b all the time for this stretch, I'm going to change this formula just a little bit. So we're going to do a little bit of a modification, and this is going to be the final form. I'm going to say, remember, we didn't talk about it much, but I could say, instead of just b to the x, I could say a times b to the x, give it a coefficient, vertical stretch or shrink. And now, instead of b, I'm going to write e to the natural log of b, but I don't like writing natural log of b over and over. So we're just going to say that the natural log of b, we'll call it k. K is a nice, k for constant, if you will, because this is called the exponential growth or decay constant. So my final form, I'm going to add that a in. I'll call it y equals a times e to the k t. And this is going to be how we're going to write these functions. And this right here is going to be the single function that gets us almost all of our exponential growth and decay models. And so, and the reason it gets us both is, remember this graph right here, the green and pink graph. If I have a positive value of b, or rather, if I have a value of b bigger than 1, then k is going to be bigger than 0. So I get growth when k is positive, and I get decay when k is negative. So if k is positive, then I'm looking at exponential growth. And if k is negative, then I'm looking at exponential decay. And we can think of k as being a horizontal stretch or shrink, and possibly a mirror, on this function e to the x. So it tells us how quickly or how slow we're going to grow or shrink. So that's k's job. Well, let's go ahead and use this. In fact, I believe we've already seen this formula, just not with the same letters. You've already seen an example of continuously compounded interest, which was y equals PE to the RT. In this case, this is exactly the same formula, but P has been replaced with the letter A, and R has been replaced with the letter K. It's exactly the same function. It does not matter which letters you call these words by, or which letters you call these variables by. They still perform the same function. So for example, if I said I want to invest $2,000 at 6% continuous interest, and I want to know how much in 3 years, I'll call that part A. Then I would say, well, my principal is 2,000. So I'd write y equals 2,000 e to the 0.06. That's my interest rate. Always has to be a decimal times t. And I want to point out something here before we go any further. This y equals ae to the kt. If I have y equals ae to the kt, and I plug in t equals 0, we call this the initial time. This is this time right here on the axis before anything has happened. And we've seen this relationship before, but just to remind you, that means y equals a times e to the k times 0. Well, k times 0 is 0, so this is a times e to the 0. And you know that any number to the power of 0, including e, is 1. So this is a times 1, which is just a. So we call a the initial value. So this coefficient right here, whether you call it p or a, it tells you how much money you have at time 0. So down here, when I say I invest $2,000, I'm investing it at time 0. Time 0. Let me enunciate that. I'm investing this $2,000. The moment I invest it, we're calling that time t equals 0. And then I'm going to find out what I have at time t equals 3. But that means that this coefficient right here can just be 2,000 because that's the initial value. So I call this 2,000 the initial value. And again, I call this 0.06 the growth coefficient. We'd call it the decay coefficient if it were negative, but since it's positive, we will be growing. Slower than if it were a bigger positive number, but still growing. So if I want to answer part A, how much in 3 years, this is a very simple proposition. It's going to be 2,000 times e to the power of 0.06 times 3. If you're plugging this all into a calculator, if you want to do it in one step, be sure to put parentheses here. Otherwise, your calculator will take e to the 0.6 and then multiply the output by 3, but you want to multiply the input by 3. So let me plug this into my own calculator. That'll be e to the 0.18 times 2,000. And I'm seeing $2,394.43. The only bad news about these models, they're very simple. I mean, you can see this was not a ton of math to go from here to here. But the bad news is there is no way to find these answers in your head. You could ballpark it by saying 6% of $2,000. What is that? I know 6% of $1,000 is 60. So 6% of 2,000 should be 120. Okay, if I just added 123 times, I would be at 2360. So it makes sense that this is a little more than 2360 from the compound interest, but not a ton more than 2360. But that's about as good as we can do trying to get a ballpark answer to ensure that our final answer is reasonable. Remember, you always want to know, is my final answer reasonable? You should have an idea before you plug it in of whereabouts you expect your final answer to be as a safeguard against typing something in wrong to the calculator. Like if I said I invest $2,000 for 3 years and I got my final answer to be 6 million, I would know something's wrong. And I hope you would too. Here's a fun problem. I could ask part B, when will our investment have doubled? That is, when will y equal 4,000? The last time I asked this question was very early in this unit, and at that point we didn't yet have the technology to answer it. But today we do. I say, okay, so y is 4,000 now, and that's still equal to 2,000 times e to the power of 0.06t. And so evidently what I need to do is find what value of t makes this equation true. So all I'm doing is solving for t. So the first thing I'll need to do is divide both sides by 2000. We get 2 equals e to the 0.06t. And the second thing I'll need to do, remember we were in this exact circumstance on Tuesday, sort of a socks and shoes situation. Next thing I need to do is undo that function e to the x that's happened to the right-hand side. We can do that by rewriting this whole thing in log form, or by taking the natural log of both sides. Either one gets us the same answer, so however you choose to conceive of it, we get natural log of 2 equals 0.06t. Now, to answer the question, when will the investment have doubled specifically, that doubling is where this 2 is coming from. So as a matter of fact, this step is always where we're going to be at on step 3 of this problem. So if you'd like to take a big shortcut, you could start here and call it the doubling time equation. Natural log of 2 equals k times t, where k is your growth constant. And then whatever t you solve for in this equation is going to be how long it takes to double. So our final step is to divide by 0.06. Log 2 over 0.06 equals t. Remember, when we divide by a number that small, that's the same as multiplying by its reciprocal. So 0.06 is 3/50ths. So dividing by 3/50ths is the same as multiplying by 50/3. So I should expect a pretty big answer here. Let's see. I'm going to use my calculator here. Natural log of 2 divided by 0.06 is 11.55. So it'll take somewhere between 11 and 12 years. And we can call this the final answer. This is just fine. 11.55 years or so. Of course, again, I don't know how many times I'm going to say this, but once again, this is a number that goes on forever without repeating. So I've just rounded it. And really, when I round, I should be more careful about using the squiggly equals for estimates. But that's how long it'll take our investment to double. We can leave that as our final answer. But humans don't talk in terms of 0.55 years. So if we were going to try to communicate this, like if our boss said, how long is it going to take our funds in this account to double? If you say 11.55 years, they kind of know what you mean. But if you're talking to a consumer, you might want, oh my goodness, I'm sorry. Excuse me. I'll be right back. I'm gonna get something to drink. I just don't understand why I am having so much respiratory trouble. I literally haven't been in contact with another human in 2 weeks, but who knows? Maybe it's allergies. Could be allergies. And now my chest hurts. Okay. But I'll power through. If I were going to give this answer to a consumer who might not be comfortable with talking about decimal portions of a year, we could tell them, well, 0.55 years is equal to 0.55 times 12 months, because there's 12 months in a year. So 0.55 times 12, it's going to be around, yeah. So it's 6.6 months. And we could even say 0.6 times 30 is 18 days. So we could say 11 years, 6 months, and 18 days. And that might be a nicer answer to give to a consumer. So that's just, you take whatever decimal part of the number is, and then I actually did it again here. Let me insert that line, 0.6 months equals 0.6 times 30 days, and that's 18 days. So that can be a nice thing to do for your end consumer if they don't appreciate units like 0.5. But yeah, we can take this as the starting point of a doubling time problem if we want. Natural log of 2 equals k, the rate of change, or rather, not the rate of change, the exponential growth rate is the correct thing to call it, times t. Any questions on this example? Otherwise, let's see, where, oh, here's a good problem. I was going to follow my notes, but I think I'll just make up examples off the top of my head. I think that'll be more fun. Again, the way that radioactive elements work is that they all have a half-life, which is to say, for example, let's say that radioactive element example 243 has a half-life of 100 years. Then, question? Oh, Mackenzie, when will my next office hours be? I don't know yet, but I'll send an email later today and let you know. Let's say we have 24 grams of example 243. So in 100 years, there are 12 grams. Half of it has decayed into other elements. In 200 years, there will be 6 grams, and in 300 years, there will be 3 grams. If I wanted, I could try to model this. A nice way to model is with graph transformations. I don't know if I've shown this method yet. It's not our only option, but it's a nice option. If I model this with graph transformations, I'm going to start with y equals... Oh, no worries, Mackenzie. I don't know yet, but I will send out an email later today once I decide. Probably sometime tomorrow then. I might do some over the weekend as well. No problem. If I say y equals 1/2 to the power of t, this is an equation that cuts in half every year. I don't want it to cut in half every year. I want it to cut in half every 100 years. So I'm going to do a stretch by a factor of 100 and say it's 1/2 times 1/100 t. That way, when I put in t equals 100, I get a half to the first. If I put in t equals 200, I get a half to the power of 2. My exponent is going to be t divided by 100. So 1 for 100, and then 2 for 200, 3 for 300. This is almost correct, but I still want to change my starting value. So instead of this, I'm going to write y equals, I had 24 grams to start with, and from then on, it's cutting in half every 100 years. So I do a stretch to meet the correct halving time, and then I do a vertical stretch so that I have the right starting value. And then if I want, I can do one more step to make the calculus people happy. I can say 1/2 is the same as e to the natural log of 1/2. And so this equation should really be y equals 24 times e to the power of natural log of 0.5, or 1/2, times 1/100 times t. And that means this whole thing right here is k. So that's one way to come up with a model for this situation. Because right now, from this table, up here, go on, up here, from this table, I can only say how much will I have in 500 years? How much will I have in 600 years? Those are easy to calculate. If you ask how much will I have in 55 years, that's going to be tough without a model. So here we've got a model, then I can just plug in 55 for t in this bottom line, and I have my answer. Alternatively, we have another strategy we can use. So pick whichever strategy you like. You don't have to know both. I don't want width. Next strategy is model by solving for k. In this strategy, I say I know my initial value is 24. So I can write y equals 24. Oh, and I will warn you, different texts use different letters than a. Sometimes they use p sub 0, sometimes they use y sub 0, sometimes they use a, but those are the three main ones. So you might see different letters there. Anyway, I know my initial value is 24. I know I want my base to be e. I don't know my growth rate k, and then k is multiplied by t. What I'll do is I'll say I have the point t comma y. I have the point, for example, in 100 years, there will be 12 grams. So I can plug that into this equation to get when 12 grams remain, 100 years have passed, and now the only unknown in this equation is k. So if I solve for k, I have a complete model. So first I divide by 24. I'm going to write 100k instead of k times 100. It just feels a little more comfortable. Now I need to rewrite this. I usually think of it as taking the log of both sides, so that's probably what I'm going to say from now on, but remember, it's either one. You could rewrite it in log form or take the log of both sides. Either way, I want you to just know that natural log of 0.5 equals 100k, and so k equals natural log of 0.5 divided by 100. And if we're going to be plugging this into our calculator a lot, we might want to go a step further. Right now, whoops, not that. Right now, I could go ahead and plug that back in up here and say y equals 24 e to the power of natural log of 0.5 divided by 100 times t, which I'll remind you is exactly the same model I got with the transformation method all the way back up here. So math is consistent. We're going to get the same answer either way. Typically, when we're doing a story problem, though, it's not fun to keep typing this whole function into your calculator every time you want to evaluate it. So typically, we'll evaluate it just once. My calculator tells me that the natural log of 0.5, if I type it in right, it'll tell me that that divided by 100 is negative 0.006931. I'm going to want at least 6 digits here. So I put 6 numbers after the decimal point on purpose. Rounding when you're dealing with an exponential function is very dangerous because that act of repeatedly multiplying over and over and over and over can lead to some very, very large discrepancies between the answer you get if you round it at the beginning and the answer you get if you didn't round at the beginning. So our remedy for that is we really want to round, but we'll give it like 6 or 7 digits just to mitigate the rounding error. It's still not perfect, but it's a lot better. If I just said 0.007, we would end up with wildly wrong answers very quickly. And so then if I write it this way, though, I can write y equals 24e to the power of negative 0.006931 times t. And that's my model. And then if I want to know how much is left after 55 years, I just plug in 55 for t and solve. I also do want to point out one feature. Notice this negative sign here. This number is negative because this is exponentially. Again, k is positive for exponential growth. K is negative for exponential decay. Here's something kind of goofy we can do with these models. Sometimes you'll be asked some, what do I want to call it? Novel questions, not the kind of questions you'd normally work with. Here's something like that. Let's suppose that you invest $15,000 and it's going to be compounded continuously, which is the kind with the E. And after 3 years, let's say we have the account reads $19,356.92. So our investment is grown. And the question then is, what was the interest rate? And I'd say that's a pretty good question. So for compound interest, I usually like to call the formula A equals PE to the RT. And then let's fill in what we know. After 3 years, so that's T, we have 19,000. That's A. This is A. Not the rate is R. We don't know R. And P is our 15,000. So the only thing we don't know in this equation is R, because remember, E is fixed. E is a number that we've known for 300 years. Always the same number, not a variable. What I can fill in then is, oh, I probably don't want the dollar signs. 19,356.92 equals 15,000 e to the power of whatever R is times 3 for 3 years. And we're going to try to find out, well, what R was. And since it's the only thing left that isn't known in this equation, we can solve for it and find its value. Again, just like socks and shoes, I want to undo the last thing that was done, so I'm going to divide both sides by 15,000. And when I do 19K over 15K, well, let me plug this into my calculator then. 19356.92 over 15,000. And again, I'm going to give a lot of digits just to make sure my final answer is as accurate as possible. I get 1.29046 equals e to the 3r. Next thing I'll do is take the log of both sides to get rid of that e. 1.29046 is 3r. And we can divide by 3. And so my final answer, if I take the natural log of this number and then divide that by 3, and I'm expecting a, what's it called? I'm expecting a number between 0 and 1. because this is exponential growth, but it's not growing very fast. I'm expecting an interest rate. So like 0.06 would be 6% interest. Now, when I actually divide this number by 3, I get 0.085 equals R, and that means our interest rate was 8.5%. Make sense? Let's see. Here's a problem that's pretty similar to this one. This is the kind of real-world problem we would see a lot. It's going to be a lot like the process we just followed. On the first day of the year 2000, the California population was 34 million. There it goes. On the first day of 2010, the Cali population was 37.3 million. Now, the way that these things go is, the way that people are born and die, the birth rate is some small percentage of the population. Every year, maybe 2 or 1% of the people in your state will have a kid. So what that means is, since that's a percentage of the number of people who are already there, if 1% of everyone living there has a kid this year, well, then that means that the number of children born is proportional to the number of parents who already lived there, right? It's proportional to the existing population. So this is a good candidate for proportional growth. As well, the death rate is a rate. If we say 1% of the population dies every year, then again, the number of people who die is proportional to how many people there are, because it's 1% of that current population. The only thing that isn't well accounted for by exponential growth is immigration, but immigration is relatively small compared to the birth and death rate, and so it's okay to use an exponential model here. I mean, it's not, if I were doing serious scholarly research and dedicating years of my life to predicting the population of California, I would use a more complicated model. But for a college algebra example, or even if I were doing like a 10-minute presentation, I would use an exponential model. It's probably going to be the best. So I would write y equals y sub 0 e to the kt. Oh, I did it without thinking about it. Again, like I said, a, y sub 0, p0, these are all the same. The reason I said y sub 0 here is I like to think of this subscript 0 as saying initial value. So y sub 0 is the initial value of y. Again, what letter you put there doesn't matter. It's just that's your initial value. I'm going to make a nice simplifying assumption. I'm just going to ignore the word million until the end of the problem, and then I'll tack on the word million to my final answer. So I'll cross both of these out, and I'll just say when t is 0, I have the point, let's see, t comma y. I have the point 0, 34, and I also have the point something 37.3. Now this is 10 years after our experiment started, so instead of putting a 2010 in for t, I'm going to put a 10 in for t because it's been 10 years. So with these two data points, the first one's going to tell me y sub 0 is 34. Easy peasy, because that's our initial value. When I plug in t of 0, I get y is 34. This second value is going to be a little more involved. This is the value we will use to solve for k. That's the nice thing about these exponential models, is they've only got these two parameters, the initial value and the growth rate. And that means whenever you have two data points, like we do here and here, since we have two data points, that's enough to solve for two parameters. We have the same number of pieces of information as we do degrees of freedom. So we're going to get a complete model. And you even see down here on the right, I ended up with, I got one parameter for each piece of information that I paid. So my first step is to say, well, of course, the initial value is 34. I'm just going to write 34 and not 34 million because I don't want to deal with all those zeros. It'll be fine. We'll say this is the population in millions of people. So that's 34e to the kt. And now I'm going to plug in this point here. I'm going to plug in t equals 10 and y is 37.3. And that means the only unknown left is the parameter k. And so I divide by, this process is going to be the same every time we do it. We divide by the coefficient, take the natural log, divide by the 10. So divide by 34. 37.3 over 34 is 1.09706. Take the natural log. And I'll go ahead and divide by 10 in this same line. So it's those same 3 steps every time. Now I take the natural log of this number, divide by 10, and I get 0.009263 equals k. And now we have a model. Now our model is whatever the population is, it'll be 34e to the 0.009263 times t. And so then I can answer some questions like, so the first step of any one of these problems before you start answering the questions I give you is to make the model. Once you've made the model, then we can answer questions like, what's the population this year? This is old data. What does it predict we'll have for a population in 2020? Well, that is 20 years after the start of the experiment. So I will say y equals 34 e to the power of 0.009263 times 20. I will pop that into my calculator. 34 e to the power of 0.009263 times 20 turns out to be 40.9. So 40,900,000 people. I'm going to go ahead and check. I'm going to Google population of California. Oh, as a matter of fact, it is only 39.51 million. So I suppose that the growth rate must have fallen off since 2010. Well, we still got very close with such a simple model. There were probably real-world complications we couldn't account for, but I'm happy with how close this is. So that's one question we can answer. I'll call that part A. Part B, when is the population 68 million? How long will it take for that to happen? And the nice thing is, this is pretty simple to solve. I said my initial population was 34 million. 68 is just 34 times. So I can use my doubling time equation. Natural log of 2 equals k times t. And we know our k. Natural log of 2 equals 0.009263 times t. So if I divide both sides by that big decimal, I'm going to get t is about 74.85. So what that means is about 75 years after the experiment. So the population will have doubled in the year 2075 if nothing changes. All right. Any questions here? Well, if not, then let's try a radioactive problem. So I showed you the radioactivity. We haven't done a problem yet. How about radon's a good one. You know what radon is? It's a colorless, odorless gas. It's also radioactive and very poisonous to your lungs. And why do I feel like I've said this recently? It seeps in from the ground into basements. So if you have a basement, you might want to get it checked for radon at some point. Some buildings have to have fans in the basements to continually pump radon out. The weird thing about radon is it has a half-life of 4 days. So let's say I have a sample. I have 90 grams of radon. That's a lot of radon. I am going to ask a couple of questions. How much radon will I have left after 3 days? Since the half-life is 4 days, I'll have 45 grams in 4 days. So I'm expecting a little more than 45 to be my answer here. I could say part B is when will only 20 grams remain? If I had said when will 45 grams remain, the answer would be after 4 days. And if I said when will 22.5 grams remain, the answer would be after 8 days. But I want 20 grams, so I'm guessing it's going to be like 9-ish days. It's good to have a ballpark in mind. Now, to solve either of these problems, we're going to want to start by coming up with a model. And now that 90 grams is going to be our initial value. Again, there's plenty of different ways. Sometimes I like to write these models as functions. So I could write something like f of x equals ae to the bx. I probably don't want to use b for that. I probably do want to use k because b means something else in this chapter. K is going to be a negative number because this is exponential decay. A, of course, is going to be this 90. So we're already halfway there. This is the model I want, but it feels like the model I have is, when I say the half-life is 4 days, what I'm saying is my function is 90 times 1/2 to the power of 1/4 t. That way, if I plug in t is 4 days, my exponent is 1, so I have half as much. If I plug in t equals 8 days, my exponent is 2, so I've got a quarter as much, and so on. So this is a way to use graph transformations, vertical stretch by 90, horizontal stretch by 4, to match the situation of the problem. The only problem is that the base isn't e, and so the calculus folks are going to yell at us. I could use this model to solve the whole problem. It's just when I go to take the logarithms, they'll all have a base of 1/2, and that's a little bit ungainly. So instead, what I'll do is I'll write f of x equals 90 e to the power of natural log of 1/2 times 1/4 times t. And because I am averse to writing that exponent over and over, I'll go to my calculator and ask, what is the natural log of 1/2 when you divide it by 4? And I'll make a syntax error, but the second time I'll get it right. Turns out that that's negative 0.173287, and I do want all of those digits just so my answer is as accurate as possible. Again, alternatively, you plugged in the data point. We'd have to be a little creative with the data point and say our data point is x comma f of x would be after 4 days we have 45 grams remaining. We could have used that information to solve for k just as well. Either way, we'll get the same answer. So now that I've got my model, I'm ready to start on part A. A, how much radon will we have after 3 days? Let's see. I'll plug in 3 for T. Oh, I mixed my, well, easiest way to fix this is to pretend I was always using T as my input variable. Your input variable doesn't have to be X, it can be T. There, and now everything's consistent. I don't want X's on one side of the equation and T's on the other. That doesn't make sense. But here, if I put f of 3, it's 90e to the power of negative 0.173287 times 3. And again, I'm expecting this to be a number a little bigger than 45 because we haven't quite passed 1 half-life. But we'll see what it is. Plug this into my calculator real quick. And I got the wrong answer for sure. What in the world did I just do? Natural log of that, now of that, 30e to that. Oh my goodness. Oh my goodness. This is why we ballpark. My calculator said 17.8. I'm not going to copy that down like a drone because I know that's wrong. I know my answer is bigger than 45. Well, as a matter of fact, come on. There it goes. My mistake was, for some reason, instead of copying down 90, I copied down 30. So let's go ahead and fix that. And now if I put in 90 times these things, okay, I get 53.51 grams. And that's exactly what I'm expecting, a number a bit bigger than 45. This is why we ballpark. Second question, I'm asking, when is f of t equal to 20? When will 20 grams remain? And again, I'm expecting a number a little bit bigger than 8 or 9 days-ish. It has to be bigger than 8 days. So I plug in my model. 20 equals 90 e to the negative 0.173287 t. And the 3 steps we do next are the same 3 steps we've been doing next every time we've done a problem like this. I divide by 90. I take the natural log, and I divide by negative 0.173287. And that's my t. It's always the same steps. First, you want to divide by the 90. Then you want to take the natural log to get rid of the e. And then you want to divide by k. It's always the same steps to get to t at this point. So not much trouble to that. So I'm going to divide that by this negative number. Now, natural log of 20 over 90 is negative, and the denominator is negative as well. So I'm going to end up with a positive answer, and hey, what do you know? I got 6797 days. Now, I'd say that this is a good deal weirder then saying 11.55 years. So I could call this my final answer, but I personally am definitely going to make the choice to report something nicer to my basement ventilation business customers. I'm not going to say your basement will be ready for occupation in 8.68 days. That would sound like a robot said it. So I'm going to say 8.6797 days. Well, that's 8 days and 0.6797 hours. 0.6797, not hours. 0.6797 times 24 hours, because there's 24 hours in a day. So I take just the fractional part. In my calculator, I can subtract 8 to just have that fraction. I multiply by 24, and I get 16.3 hours. Well, 16.313 hours if we're being precise. And I could even go a step further and say 0.313 hours times 60 gets me the number of minutes. So I'll take that and multiply by 60, and I get about 19 minutes. So if I really want to impress this customer, I'll say 8 days, 16 hours, and 19 minutes. Or maybe I could give them a specific time of day that their basement will be ready. If I know when is it going to be 8 days, 16 hours, and 19 minutes from right now at 9:02 a.m., I'd be like, all right, your basement will be ready on April 25th at 1:21 a.m. Like, how do you know that? I really paid attention in college algebra, ma'am. That's our business guarantee or whatever. So there you go. There's a model for exponential decay. Let me do one more exponential decay, and then maybe we'll do a bacteria. Just want to knock out these models here. Probably the most famous example of exponential decay is carbon dating, which is not spending some time with carbon on a Friday night. Carbon dating is where I dig up some bones at maybe at some kind of Bronze Age site, and I want to be able to fit these bones into the chronology of the history of the place. So I need to know how old these bones are. Now, the good news is that the bones contain carbon. Now, here's how this works. As long as I'm alive and as long as you're alive, we are continually breathing air from the atmosphere. Now, the air in the atmosphere contains carbon dioxide. So we are getting carbon dioxide from the atmosphere. Of course, the other big source of carbon in your body is from the food you eat. Carbon-based, there's a reason we call Earth life carbon-based life. Everything that's alive on Earth is made of carbon, but you know where it gets that carbon? From the atmosphere. If you're a person, if you eat a hamburger, that hamburger has carbon in it that came from the cow. And the reason the cow has the carbon is because the cow ate the grass. And the reason the grass has the carbon is because the grass grew out from nothing by using sunlight to convert the carbon dioxide in the air into part of the grass. So it all comes from the carbon dioxide in the air. All of the carbon in your body, it comes through the food chain from the atmosphere. And the way the atmosphere works is that almost all of that carbon is carbon-12. It has 6 protons and 6 neutrons for a total of an atomic weight of 12. But when carbon-12 is way up in the top of the atmosphere, way up in the stratosphere, high-powered beams of sunlight can cause that carbon-12 to spontaneously take on 2 extra neutrons and become carbon-14. Now, carbon-12 is stable. Carbon-14 is radioactive, as in carbon doesn't actually enjoy holding 8 neutrons, and every so often, a carbon-14 atom is going to just shoot a particle straight out of it. If I recall correctly, those are, oh, now I don't remember which kind of particle. Either way, it blasts a particle out so that the nucleus can get a little lighter and breathe a sigh of relief. And so here's what this means. As long as you're alive, you're breathing in the atmosphere and eating food that's all made of carbon-based life. And so for as long as you're alive, your carbon is being interchanged with the atmosphere's carbon, maybe through a few intermediaries like cows, but since the ozone layer is creating carbon-14, and then the carbon-14 is decaying back down, those two rates balance each other out, and there's a steady ratio. There's a lot of carbon-14. I think so. I think it's an alpha particle. Yes, thanks, Samuel. There's a lot of carbon-14 in the atmosphere, or there's a lot of carbon-12 in the atmosphere and only a little carbon-14. And while you're alive, the ratio of 14 to 12 in your body can be computed from the ratio of 14 to 12 in the atmosphere. It'll be higher than the ratio in the atmosphere, but it'll be a predictable ratio. So living things have a very, very predictable ratio of carbon-14 to carbon-12. As soon as you die, you are no longer eating, you are no longer breathing, and so you no longer have any new sources of carbon-14, and that carbon-14 in your body is going to decay via alpha particles, you say? Let's go with alpha particles. It's going to decay, and so all of your carbon-12 stays because it's completely stable as long as we know, but the carbon-14 is going to slowly dissipate. And so if I find an old dead dude's bones, and I take a little sample, scrape it off, go back to the lab, and analyze it in a mass spectrometer to find out how much carbon-14 is left in it, if I find the ratio of 14 to 12 in the dead dude's bones, well, that tells me how long he's been in the ground, not eating, not breathing, just slowly decaying his carbon-14. So, since we know that the half-life of carbon-14 is a very, very predictable 5,730 years, I can use this cycle and the fact that living things exchange but dead things don't. I can use that to find out exactly how old these bones are. Same thing works for wood, because trees have a predictable ratio of 12 to 14. So if I measure the ratio of 12 to 14 in, say, a picture frame, I can tell you when that picture frame was turned from a tree into a picture frame, and that establishes a maximum age on the painting inside. So all sorts of convenient ways to use carbon dating. Now, the bad news is it doesn't work on stone tools, but the good news is if you find the stone tool next to a fire pit, you can use the wood in the fire pit to the same purpose. So most of the time when we find human artifacts, we can use carbon-14 to see how old they are. The bad news is it doesn't work for really, really old stuff, because after about 12 half-lives, or after about 6,000 years, the amount of carbon-14 is left is so small that we can't accurately measure it. So carbon dating works up to a threshold of about 60,000 years, and the further back you go, the bigger your error bounds are. Like, if I'm looking at something from the Bronze Age, I'm going to be able to establish its age within about 30 years, which is amazing. But if I go back 60,000 years, I'm going to be able to establish its age to within like 100 or 200 years of accuracy. The good news is there's like 20 other radioactive elements that we can use as clocks in the same way that we use carbon-14 as a clock. And so since we have so many different elements and we can sync up the clock of one to the clock of another, that's the miracle, is that, I mean, it's what you'd expect, but it's a wonderful confirmation of the theory of radioactive dating that all 20 of those radioactive clocks are consistent with each other. And so we have an unbroken timeline. We can even test rocks that are billions of years old to see exactly how many billion years old they are. It's all very neat. So let's say that I dig up an ancient Roman dude, and the ancient Roman dude has turned into a skeleton, And that skeleton has 76.6% carbon-14 remaining. As in, I scrape off a sample and I see that the ratio of 14 to 12 is 76.6% of what it should be for an alive dude. Then the question is, how old is the skeleton? So I'm going to use my model. Let's use y equals y0 e to the kt. I'm expecting k to be negative. I'm going to say that my two data points are at 0, we have 100% of the carbon-14. And after, however long it's been, we have 76.6% of the carbon-14. So that's not a data point. That's something to solve for. But what I do know is that after 5,730 years, 50% of the carbon-14 will be remaining. So I have two data points that already are solved for that I can use to estimate my parameters. So the first one just means that my initial value is going to be 100. This last one is going to help us solve for k. And of course, I could also use graph transformations, but I want to show you both methods. So first I'll write equals 100 e to the kt, and then I'll plug in this data point, and I'll write 50 equals 100 e to the 5730 times k. We've seen these steps a dozen times today. 0.5 equals e to the da-da-da, 5730k. Natural log of 0.5 equals 5730k. Natural log of 0.5 over 5730 equals k, and that's approximately 0.000121, but it's negative. Negative 0.000121. It's decay, so k is expected to be negative. And now I'm ready to use this 76.6 number. I say y equals initial value 100. Oh, and I know why. Y is 76.6 equals 100 e to the negative 0.000121 t, however long it's been. Would you look at that? It's time for the same three steps. I divide by 100. I take the natural log, not 7, 6. And I divide. And then I plug that into my calculator. Well, I'm missing a page of my notes, so I actually will plug it into my calculator instead of reading it off of paper. Good thing I have my calculator. 76.6 divided by 100, all divided by negative 0.000121. Now in my calculator, I got 2,203.08, but we can't really report this result with that much accuracy. I'll just say this Roman person definitely died between, I don't know, around 2,200 years ago, somewhere between 2170 and 2230 would probably be a good guess. Either way, I know that this person lived in like the 2nd or 3rd century BC. And that allows me to contextualize these remains in the context of the Roman Empire at that time. Roman Republic at that time. It wasn't an empire until later. But that allows me to understand these remains in a historical context and learn something about history. So that's carbon dating. It's one of our best tools for archaeology. All right. And that's all the time we have for today. So thank you both for coming. Any questions before we head out?
Well, if not, then let's adjourn this meeting.